Good evening and welcome to this new tutorial on absolute motion analysis. In this tutorial I'm going to solve this problem from Hibbeler's book, 13th edition, example number 16-49. In your class notes, this is in lecture 14, example 3 on page 7. So I'm going to solve this problem involving two bars. One of them is connected to a fixed point and the other one is connected to a slider. Beam AB is rotating counterclockwise on this direction, making beam BC to move up and to rotate also counterclockwise, and in the end of the day making the slider to go up with velocity and acceleration that we need to find out according to this question. When theta here equals to 60. So to make things convenient and clear for ourselves, we can create from this system 90 degrees angles, 90 degrees to be more specific, 90 degrees triangles. So first I'm going to draw this line in a way that I can make an intersection with this one. Okay, and say okay, I have this one, and I'm also going to create another triangle that helps me to relate the horizontal distances to each other with respect to the moving bars. Okay, here we go. So this bar, by the way, is equal in length to this bar. Both of them equals to L, and this also is L. So from here to here plus from here to here is equal L. That's pretty good for us to deal with. We can name this length to be A. We can name this length to be B. Okay. And we can say the total length here is equal to A plus B. So I'm going to write this down, all equal A plus B. Now we can name this angle to be phi, and we can say A is equal to L cosine theta. So L here originally, this one, is equal to L cosine theta plus this one is equal to L cosine phi. So we came up with the relationship now from the lengths here. We can get rid of the L's here and we say okay, 1 equal to cosine theta plus cosine phi, and we are good now with this relation. The summation of the cosines of theta and phi equals to 1. That's good relation to keep. What we can do here is to do the derivative for this relation to find and produce the omega, or the angular velocity of this bar and the angular velocity of this bar. So we can do the derivative for this twice to come up in the end also with the angular velocities, with the angular accelerations of this beam and this beam. So we can write this down. The derivative of 1 is 0, of course, and this would give us the minus sine theta times theta dot minus sine phi times phi dot. And this is equation number 2. This helps us. We can make the derivative further for this relationship to give us the accelerations. So we can keep the minus out and do the derivatives. Sine theta double dot plus cosine theta theta dot, again theta dot, and we say minus sine phi phi double dot plus cosine phi dot again, and we rearrange everything here to come up with the relationship here to be 0 equal to minus sine theta double dot minus cosine theta times theta dot squared minus sine phi double dot minus cosine phi dot squared. Now we know already that this bar is rotating with a constant angular velocity. This means that phi double dot is 0. The angular acceleration is 0. So we can get rid of this and refine the equation to be, so we can get rid of this term and refine the equation to come up with this relationship. Minus cosine theta times theta dot squared minus sine phi double dot minus cosine phi dot squared equal to 0. And this is relation number 3. Now we need to do the calculations when theta now is equal to 60. So we can get advantage of this relationship and say, okay, 1 equal to cosine 60 plus cosine phi, and we can rearrange things here to be cosine phi equal to 1 minus cosine 60, and this would yield for us phi equal cosine the inverse of 1 minus cosine 60, and this would give us phi to be equal to 60 degrees. This is good. This is good. Now we know the phi here is equal to 60. So let's keep ourselves with finding the angular velocities. So we can use this equation number 2, to also to know more about the angular velocities. So from equation number 2 we can write this down. 0 equal to minus sine 60, I'm sorry, theta dot minus sine 60 times phi dot, and because of the everything here would give us in the end of the day theta dot equal to minus phi dot. This is, so cancelling this up would give us this relation. So the angular velocities are equal, but they are opposite. They are just opposite in signs, but they are equal. Now we need to go further and go for the angular accelerations. We can use this equation number 3. We can go and say, okay, minus cosine 60 times theta dot squared minus sine 60 times phi double dot minus cosine 60 times phi dot squared equal to 0, and rearranging things here would minus, this equals to minus cosine 60 theta dot squared minus sine 60 phi double dot minus cosine 60, and this is minus theta dot squared equal to 0. Going to the second page here, so I would write this down to say minus cosine 60 times omega squared minus sine 60 times phi double dot minus cosine 60 times omega squared equal to 0, and this would give us in the end of the day minus 2 cosine 60 times omega squared equal to sine 60 times phi double dot. Okay, so this is the relationship that now we have. Rearranging things here would give us phi double dot to be equal to minus 1.154 omega squared. So the angular acceleration of this bar BC or CD is equal to this value, So now we have a full set of information about the omegas of this beam, of this bar and this bar, the angular accelerations as well. We need to understand the situation more in terms of the displacement of the slider, because this is an absolute motion analysis. We need to relate the motion of the slider to the angles of angle phi and angle theta. So how we can do that? It's pretty easy. We can get the ruler again and say, okay, we know already from the 90 degrees triangles that if we draw this, okay, so we can say this is easily equal to, so this line, this vertical line is equal to this line is equal to L sine theta. We know that already. Now if we want to continue this line, this is phi, and the entire line here, I can write this down for you and say this is L sine phi. Okay. Now, if we assume that this slider was here, so it was at this position, we can assume that. We can say the slider was here in a certain way, was here. So it moved down to this distance. It moved down to a distance x. So in fact, now the entire length here is equal to this length. The entire length here is equal to this length plus this length, which is x. So we can write this down and say L sine phi is equal to L sine theta plus x. Right? And we can rearrange this because we are focusing on the x here. So we can say L equal to L sine phi minus L sine theta. Right? And we can take this L out and say L sine phi minus sine theta. All right. So this is very important relation. This is a very important relation. It gives us the displacement of this block in terms of the angles theta and phi. So we need to come up with the velocity now. So we can do the derivative, the velocity also as well as the acceleration. So we just need to do the derivative twice here. So we can say V equals to L cosine phi times phi dot minus cosine theta times theta dot. All right, so this is the velocity. Now with the acceleration is going to be somehow a bit long equation, so I'm going to be a bit careful here in doing the derivative. L here equals to cosine phi times phi double dot plus minus sine phi times phi dot. I'm going to close this, and then I'll say, okay, this is phi dot. I'm going to close this, and I'm going to continue and say minus, and open up, say cosine theta, theta double dot plus minus sine theta, theta dot times theta dot. I'm going to close the parentheses here. So this is the displacement, this is the velocity, and this is the acceleration. I'm going to rearrange this relationship carefully, and I would come up with this relation, L phi double dot cosine phi minus L phi dot squared sine phi minus L theta double dot cosine theta plus L theta dot squared sine theta. So I have now a relation that would allow me to calculate for the velocity and as well as the acceleration. Now I have some parameters I can use. What the parameters are: theta equals 60, phi equals 60, theta double dot is equal to 0, phi double dot is equal to minus 1.154 omega squared, and theta dot, which is omega in fact, equals to phi but in minus sign. So I'm going to use these parameters to substitute them in the equations of the velocity and the acceleration. For the velocity now, for the velocity, v equals to here's the equation, so I wouldn't need to write it down again. I'm just going to substitute. I'm going to say cosine 60 times minus theta dot minus cosine 60 times theta dot. This would give me v to be equal to minus L theta dot to cosine 60, and this would give me v equals to minus L theta dot, and this is the velocity of the slider here. Now for the acceleration, I just can substitute the values of the acceleration in a new page here. So I already have the equation of the acceleration. I'm just going to substitute the values. So a here equals to L times minus 1.154 omega squared cosine 60 minus L times minus omega squared times sine 60 minus L times 0 cosine 60 plus L omega squared times sine 60. Rearranging things and doing things here would give us, in the end of the day, a equals to minus 0.577 L omega squared. So the minus sign means that the slider is in fact going at least the direction of the direction of the acceleration is up. So it is kind of decelerating, And if we look again to the sign of the velocity, it is also minus. So the slider is actually going up. The slider is actually going up in the opposite direction of the assumed positive direction of x, of the displacement. So the slider is going up, and it is not decelerating. It's going up, and the acceleration, the direction of the acceleration is in the direction of the velocity. So we can we can write this down again and say a is equal to 0.577 L omega squared, but it is in the upward direction. Thank you for watching.